Good afternoon, I am Kareem Zgana, and welcome to Build Your Own E-Meter deep dive session. So we're going to do a few things today. First, I'm going to give an introduction to energy metering, talk about the basics of e-metering, and then Bart's going to talk about the different power supplies. From there, we're going to talk about why choose the MC430 for metrology, the different e-meter SoCs that are available. Meter calibration is important, and then Bart is going to go over the lab portion. So I'd like to start by asking, what is energy? Energy is required by everything that's performing any sort of task, including us humans. And it's created for different tasks, and there are many sources such as gasoline, which powers all modes of transportation, from cars to planes to even lawnmowers, to electricity, which powers most equipment inside a home and office. Also, coal is another popular alternative. And we're now at a time where the amount of energy that we need is increasing, however, the amount of energy that we have is decreasing. And as a result, energy is extremely precious. And lawmakers are instituting laws to actually help conserve energy. So since energy conservation is important, it's also important to be able to measure energy accurately. And that's basically what an energy meter does. It measures the amount of electrical energy that is consumed. It does this by calculating instantaneous power, which is the product of instantaneous voltage and current, and then integrating it over time. So there are two types of energy meters that are used today. The first type is electromechanical meters. Most homes have these meters. They have been around for more than 100 years. They operate by counting the number of revolutions of an aluminum disc. And basically, it's set such that the amount of revolutions of the aluminum disc corresponds to how much energy is consumed over a set given time. So the faster it spins, the more energy consumption that corresponds to. And one limitation of this meter is that in order to take readings, you have to physically go to the meter. And since there's a dial interface that is limited in accuracy. The second type of meter is electronic meters. It's extremely favorable metrology with absolutely no moving parts. You have actually current and voltage sensors and microcontrollers, DCP processors to actually use the current sensors and voltage sensors to calculate the power as necessary. And one advantage of this type of meter is that self-energy consumption is negligible, which puts less of a strain on the electrical grid. And also, it has a digital display, which provides more accurate measurements when compared to the electromechanical meters. Another feature is that with electronic meters, you can actually determine when a meter has been tampered with and take the necessary actions as needed. Also, electronic meters have support for automatic meter reading, which is a one-way communication from the meter to the outside world, and advanced meter infrastructure, which is a two-way communication from the meter to the outside world. So there are three types of measurement configurations. The first type is single-phase measurement, which is common in most residential complexes. You basically have one voltage and one current, and this is used to support low to medium loads. The second type is dual-phase measurements. This is not common, however, Japan uses this. And in this case, you have two voltages and two currents, and each phase is 180 degrees out of phase with the other phase. The third type is three-phase measurement. This is common in large office spaces and industries. You have three separate phases to distribute AC power, and each phase is 120 degrees out of phase with others. And this is used to support large loads. So now that we gave an introduction to the energy meter, let's dive more deeply into the basics of e-metering. So the figure on the left shows how an e-meter will be connected to the line and neutral from the utility companies. And basically, you have the line and neutral. You have to have the voltage sensor in parallel with that. And the current sensor has to be in series with the line or neutral wires. And basically, the figure on the right shows, the figure on the left expanded to show the current sensors. And the current sensor would translate the current drawn by the load to a range that, to a voltage that the analog to digital converters can actually sense. Then you have the voltage divider, which divides the mains voltage to a range that can also be sensed by the analog to digital converter. So there are various metering parameters that are calculated. There is active power, which is the amount of power that is delivered to the load, reactive power, which represents loss, and apparent power, which is the vector sum of active and reactive power. By accumulating this over time, you get active, reactive, and apparent energy. Also, there's the power factor, which is a measure of the distribution, the efficiency of the electrical distribution system. There's the peak max voltage and current, the root mean square voltage and current, the frequency of the system, and also the temperature of the system. So this slide shows how the various mean parameters are calculated. For root mean square voltage, you basically take each individual voltage sample, square it, accumulate it over time, take the average, and then take the square root. Similarly, for root mean square current, you do the same thing except with current samples instead of voltage samples. To calculate the average active power, you take each voltage and the current sample, multiply them together, accumulate it, and take the average. For the apparent power, you multiply the root mean square voltage by the root mean square current. And there are two ways to calculate the reactive power. First way is by taking the apparent power square, subtract the active power square, then take the square root of that. And the second way, which we actually use in our metrology algorithms, is to shift the voltage samples by 90 degrees, multiply it by that particular current at the instance, accumulate over time, and then take the average. Power factor can be calculated two ways. One is by calculating the cosine of the angle between the voltage and current samples, and the other way is by doing active power divided by apparent power. So there are two ways in which NG is translated. The first way is by using digital display, which is good enough for installed meters. However, it does not truly reflect the accuracy of the meter because there are only so many digits that you can display. There's also the pulse output. This is what's actually used to determine the meter error and is used for calibration. And basically you have pulses that are outputted at a rate proportional to the amount of energy consumed. So if you have high energy consumption, you have more pulses in a given amount of time than when you have a low energy consumption. And one option is to actually have an LED on the pulse pin so that instead of having to physically connect to the meter, you can actually just use a optical sensor to sense the pulses as necessary. So in order to sense mains voltage, you have to divide that down. And basically for the voltage sensor, that's what it does. And you use a voltage divider for the voltage sensor since it's simple and extremely cheap. And basically you choose the values of the voltage divider to properly divide the mains voltage to a range that the ADCs can sense. No level shifter is necessary for this type of sensor since if you have differential inputs, all you're doing is dividing down the magnitude. Also, a gain amplifier stage is not required because if you want to change the gain, you can simply change the values of the resistors in the voltage divider. And this actually shows the voltage front end on our F6736 EVM, which you guys will have a chance to play with. You have R6 as the varistor for voltage spike protection. L1, L2 are EMI filters. And you have the voltage dividers of the R11, R16, R17, and R18 are the voltage divider circuitry. And basically you have a 990K resistor series with 3K resistor. And the reason why the 990K resistor is split into 3 different resistors is to prevent sparking. And on the front end, you also see the anti-aliasing filter. So there are multiple types of current sensors that are used. Shunt is one commonly used sensor. It's based off of Ohm's law. And basically, the voltage that's fed to the analog to digital converter is equal to the current drawn by main, current drawn by the load, multiplied by the resistance of the shunt resistor. And one advantage is that this is a very inexpensive solution. And since you have a relatively large current and a small maximum voltage that the AC can sense, you have the shunt resistor always in the range of micro-ohms. Another advantage is that there's no magnetic effects with this type of current sensor, and there's absolutely no inherent phase shifts. Some disadvantages of this type of sensor is that it can only be used with single-phase measurement systems. And since during self-heating, the actual value of the resistance can change, this can affect accuracy at larger currents. So the second type of current system I'm talking about is the current transformer. This provides electrical isolation that protects the device. And basically, the current, the voltage that is sensed by ADC is equal to the current flowing through the primary divided by the turns ratio multiplied by the resistance of the burn resistor. And this type of sensor provides the best accuracy. However, there's some disadvantages in that it causes a phase shift that has to be compensated for in software. And it could be susceptible to external magnetic effects. So actually, some people, what you could do is, if you have a magnet applied to that, to the CT, it could actually cause saturation, which will affect the readings, the current readings. So this slide shows the third type of current sensor, Rogowski coils. They are simple devices for measuring currents based on Ampere's law. Basically, you have a magnetic field produced by the current flowing to the conductor, and that causes the output voltage proportional to the rate of change of current. Now, this has to be integrated, so that's one disadvantage in that you either have to have external circuitry to form analog integration or do it in software using the CPU. Some other disadvantage is that it's position sensitive, and it is hard to find the best match. This actually shows the current front end on our F6736 meter. You have diodes, clamping diodes on the end, and a two-way diode, I think it says D10, just in case the burn resistor fails, because the burn resistor was failed, then that would cause a large voltage on the measuring device, which can damage it. There's also the anti-aliasing filter circuitry at the end. So that concludes the basics of e-metering. And for the power supply section, Bart will cover that.
There we go. So I know everyone here are all digital engineers now, probably don't care too much about power supplies, but for e-metering, since we do a lot of analog measurement, they're incredibly important. We need to make sure that we have really stable VCC rails that don't ripple too much, because any noise injected in this can really reduce the readings that we have coming out of the ADCs in our final calculations. So a lot of these meters, I mean, when companies are deploying millions of them, they're going to be pretty low cost. So end customers don't really want to put a lot of effort into doing power supplies and things like this. So we have to offer them solutions that don't require many components. And that works well because the MSP430 is pretty low power. So we don't really need a really big beefy power supply on a lot of these. In some areas, anti-tampering features are important. So avoiding magnetics like transformers and the like are really useful as well. McCray mentioned earlier that these new smart meters have a lower burden on the grid. So we need to make sure that we don't have any wasted power. So efficiency is really nice on these as well. When you're putting 1,000,000 meters at a watt, I mean, that's a megawatt of power coming out there that the grid has to be able to compensate for, that they won't be able to bill to the customers either. These things are also pretty small, so we need to be able to keep board space limited. There's a lot of isolation requirements. So there's a couple different things that we have to worry about here that go into these power supply designs that are pretty specific for these high voltage e-meters. But we have a couple different options available currently though, and we have reference designs for these, so you don't have to worry about designing them yourself. We have a capacitive based, which is a simple cap drop supply, switch mode power supplies, and then the larger transformer based ones. So when it comes down to it, your power budget is going to be dependent on the number of features you have enabled on your meter. So when you do a simple single phase low end meter with just an LCD, you're only drawing 6 to 8 milliamps. So that's a pretty easy thing to power. It's basically just the MSP running and all the peripherals on there as well. Whenever you start doing things like RF with the AMI communication, you're really going to crank that up. A lot of the power is going to be going to the wireless chip. Luckily, TI offers some pretty competitive low power wireless chips, but we're still looking at something in the 50 milliamp ballpark. If you crank this up to just a simple three-phase meter, so for some of the corporate installations, or even if you're just doing a meter that'll do a local office or an installation, or even just a piece of machinery, so if you take this down to a sub-metering level, you have to do more with the sigma deltas and the ADCs, and your CPU is running a lot higher, so you're looking at something in the 16 milliamp range. You'll notice it doesn't scale linearly from the single to three-phase meter because there is a core we still have to power. There's a lot of overhead on these. Then again, whenever you add RF, you're looking at more power that's required on here. More data has to be sent out with the three-phase meters. So this is the simplest, lowest cost power supply we have, and it'll only do about 10 to 15 milliamps coming out. It's just a cap drop supply. The line, so this is 230 volts coming in. It's just clamped, rectified, and filtered and ran right through an LDO. So it's really brute force, really simple, but it gets you your 3.3 volts that you need to run your core. This can be used on other applications as well. The biggest disadvantage is, beyond the power limitations, is that this is not isolated. So this is essentially, as you can see here, your ground is connected straight into neutral, and your line voltage is only blocked by a diode coming in. There's no galvanic isolation between your 230 volt line and your 3.3 volt. So this can make actually working on the board pretty dangerous. So if you're working with a customer that's designing a power supply, they need to be quite aware on these. The board in front of you has a different supply design with a buck converter on it. So this is a new design out of the power group. It's slightly more efficient. It's very similar. We have the cap drop supply input rectified, but we're using a more advanced circuitry here with the buck converter, which makes it a lot more efficient. So we're able to pull more power off the line with a smaller actual component size on here. This can be good up to about 45 to 50 milliamps. So you can run one of the low power RF chips off of this as well, which is really nice, especially if you have it on a 230 volt line in some of the international areas or some of the polyphase meters.
It's still not isolated, right?
Correct. Again, this is unisolated. The one on the board here in front of you, if you put 230 volts into this board, it can be very, very dangerous very quickly. Luckily, the ones here are modified. I'll talk about that more later. So with this buck converter, it's a little more reliable. It's still low cost. It costs a little bit more than that super basic one, but it sure beats putting some large magnetics on the board. So, however, if you want the full-blown big power supply, if you have to run, if you want to put Wi-Fi on a meter for whatever reason, you're looking at transformer-based supplies. So these are pretty straightforward. We have a lot of reference designs for these already to bring 110 down to your 3.3 volts. So you can do cascaded regulators, whatever you want here, full rectification, full transformer. So these are fully isolated. They make it a lot safer on the board as far as your digital buses go. You're still going to have full 230 volts coming into the meter itself, but you can do a lot more protection with this. So this increases your power output. It's also going to increase your line load. So this VA burden, it's whenever you have a phase shift on your line. So this can induce some weird effects for the grid. The other ones are more linear, so which are a little preferred, but for whenever you have to crank a lot of juice in your meter, this is really handy. Regrettably, of course, transformers are expensive and bulky, especially when you're doing a three-phase meter. Part of the ANSI requirements and IC requirements, if a phase drops out, it still has to run. So you have to be able to pull power from all three phases simultaneously, or two, or one. So that means you're going to need 3 transformers, 3 bridge rectifiers, and this can get pretty costly pretty quick. And if this would go. There we go. So that's the basics of power supplies. Those are really the big 3 options that we have. There's reference designs available for all of these. So like I said, if you don't want to design your own, but it's good to be cognizant of what kind of requirements your customer is going to need. I know especially here in North America, we're seeing a lot of sub-metering customers come out. So the cap drop supplies are going to become pretty popular. Luckily, the Power Group has a couple good reference designs that we've used on our boards as well. They've been verified and vetted. So if you need any help choosing some of these, you can definitely come to us and we can point you in the right direction. So I'm going to hand this back to McCrae, go over some of the more SOC features.
Thank you, Bart.
Oh, sorry, got questions.
Yeah, so if you want to see the reference design, where do you go?
So personally, I actually just searched Google for cap drop power supply design, and the first one is a TI app note that was published about a year ago, and that's the latest one for the cap drop supply. If you pull up any of our e-meter reference designs, we'll have a power supply section in there, and that'll go through the schematics. And the power supply group, if you have any friends in the analog industry, they can definitely help you with layout and component selection if you want a little more customization on there. Anyone else?
So now that we talked about the basics of e-metering, let's talk about why choose the M230 for metrology. So this shows our M230 e-meter SoC solution, and basically you have current and voltage sensors which translate the voltage and current to a range that the ADCs consents. And the hardware multiplier would take the voltage and current samples and multiply them together to calculate the necessary metrology parameters. After these parameters are calculated, they are sent to the LCD driver for display, and also to communication peripherals for wireless or wired interface, communication. There's also a real-time clock for keeping track of time. So why choose the M6330 for e-metering? The M6330 has a powerful 24-bit sigma delta converter. Also, it has up to 32-bit by 32-bit hardware multiplier, which allows you to do multiplications more quickly. Also, there's a real-time clock for keeping track of time. Integrated LCD controller for displaying things on the LCD. There are some advantages in the low power features of the M6330 in that since power in active mode is low, this allows you to have a cheaper power supply. And also since power and low power modes are also low, this allows you to run off of a battery for a longer amount of time. If there's an additional ADC that's available, you can use this for measuring the current through a neutral wire, and this can be used to determine if the meter has been tampered with. Also, on some devices, there's actually a CPU-independent metrology engine called the ESP430, which allows you to perform, so the ESP430 would actually perform metrology calculations independently from the CPU, which allows you to use it for more host processor functionality. So in the M6330 Sigma Delta ADCs, it operates in 24-bit mode, and it's a second-order architecture, and basically you have a modulator which modulates the analog input using the reference voltage and the modulation clock. And this produces a bit stream that is fed to the digital filter. And the digital filter would average a certain amount of these bits to produce one effective sample. And this is the amount that is averaged to produce one effective sample is called the oversampling ratio. Another feature is the oversampling ratio on Sigma Delta could be up to 1024, and sampling clock is up to 2 megahertz, which allows you to have, the modulation clock could be up to 2 megahertz. There's also software selectable internal-external reference, integrated temperature and or battery voltage. Another feature is that there's a inbuilt programmable gain amplifier, which allows you to magnify the output of low voltage current sensors such as shunts and Rogowski coils. Also, the Sigma Deltas have differential inputs, which is very good for AC measurements. This allows you no need for a level shifter, which thereby simplifies the analog front-end circuitry. Also, there are multiple converters that can occur simultaneously, which since they occur simultaneously, there is no inherent delay between the voltage and current samples. Therefore, unlike sequential sampling, you don't have to have software compensation for sampling multiple converters. So this block diagram shows the SD16A, SD24A modules, which is available on the M6330 F47X4, F471XX, and AFE2XX families. This portion is, this bottom portion is replicated for each channel. You can have 30 kilohertz to 1.1 megahertz modulation frequency. And the source for the modulation clock could be M clock, SM clock, A clock, TA clock, and there are necessary dividers to divide them down. There's also integrated temperature sensor and AVCC measure. So there's a maximum range that the ADCs can sense, and this is defined by the full scale voltage. And on the 4XX family, this is calculated by taking the reference voltage, dividing that by 2, and dividing that by the PGA gain. And actually, the 6XX family, that's you have even higher full scale range because it's VREF over the program gain amplifier as the actual equation. Now, we recommend that you basically build the front end so that the maximum voltage fed to the ADC is equal to about 80% of the full scale range. So for instance, if you have a gain of 1, then you have full scale range of 0.6. So you should build the front end so that the maximum voltage fed to the ADC is 0.5 volts. So there's also a hardware multiplier module on e-meter SoCs, which is ideal for calculation of voltage and current. There's signed and unsigned multiply, signed and unsigned multiply and accumulate. And there are two types. There are 16-bit hardware multipliers or 32-bit hardware multiplier, which one is available is dependent on the actual chip. Also, on some devices, there's a DMA trigger so that whenever you perform multiplications, you can directly send the results to memory. So in our metrology software, we basically have 5 main parts. The first part is the initialization include file, and basically in this file you have a whole bunch of if-defs, and based off of what features are defined, you can change the functionality of the meter. And based off of which if-defs are chosen, the source code that's compiled is changed. There's also the source code for setup initialization, which initializes the clocks and peripherals. There is the background process, which occurs every ADC interrupt. And basically, in this process, for each sample that arrives, you update the working parameters for metrology variables. And also in the background process, pulse generation that's where it's done. In the foreground process, once you have approximately 1 second of data, you compute parameters that require actual updates, such as VRMS, IRMS, average active power, average reactive power, and so on. The 5th part is the GUI communication, and the GUI is used for calibration and also for displaying the parameters of metrology parameters. This flow diagram shows the background process, and basically you have interrupt once every 4096 at a rate of 4096 hertz. Once you have interrupt, you read the voltage, you read the currents, and once you have the voltage and currents, you remove the DC using a DC filter, and you accumulate the square of the current and also the square of the voltage. Also, you multiply the voltage and current together to get the instantaneous power, and you accumulate that. Whenever there is a zero crossing, you update the calculation for frequency, and you also, based off of whether current is lagging or leading, whenever there's a voltage zero crossing, you update information on whether a load is inductive or capacitive. After approximately 1 second of energy has been calculated and it's a zero crossing, then a flag is asserted to notify the foreground process that the foreground can now calculate the metrology parameters. Also in the background process, you perform pulse generation. So are there questions so far on? So far, are there any questions? No. All right. In the foreground process basically takes care of the initialization of the hardware, the clock, the SE24B, and the other peripherals. And once 1 second of energy has been accumulated, the background process would notify the foreground process to use the working parameters from the background process to calculate the metrology parameters, such as RMS current, RMS voltage, active power, apparent power, reactive power, frequency, and power factor. Also, at that point, the LCD is updated to display the next parameter. So for pulse generation, in the actual active power register, 1 kilowatt hour threshold is defined as this number, and based off this number, a tick is calculated. And the tick is calculated based off of a pulses per kilowatt hour setting that's set in the software. And whenever you accumulate energy, you accumulate the energy of the previous, you accumulate the calculated energy from the previous frame, and you accumulate it. Once the energy accumulator, you have enough energy that corresponds to 1 tick, then 1 pulse is generated, and also the energy accumulator is subtracted by the amount that corresponds to 1 pulse. So now that we talked about the features of the MC30 for metrology, Let's talk about the newest E-meter SoCs that are currently available. But first, before I begin, are there any questions? Question? No. So the MC30 F672X and F673X devices are the newest E-meter SoCs for one-phase metrology. And they can also perform tamper detection whenever you have 673X devices. They have a clock frequency up to 25 megahertz, up to 128 kilobytes of flash, 4 kilobytes of RAM, and 50% power reduction when compared to the 4XX family. There is up to 3 24-bit sigma deltas and a 10-bit SAR ADC. So you could either use the sigma deltas for one-phase metrology with tamper detection, or you can couple it with 10-bit SAR ADC for a cheap 3-phase solution. Also, there are 40 segment pins, LCD segment pins, and whenever you run on a MUX mode, you can drive up to 320 segments. In addition, there is a RTC module with temperature compensation, up to 3 UARTs and 4 timers, and there's support for LPM 3.5 mode. There's also CRC16 module for data checking and a port mapping controller for flexible port pin to peripheral mapping. One other important module of the 67XX family is the aux module, and this allows you to power the meter from an alternative source than the one that is connected to AVC or DVCC. So for instance, the use case for this is whenever there's a power outage, you can still run the meter off of a backup battery. The MC30 F67XX polyphase E-meter SoCs have many enhancements from the single-phase E-meter SoCs in that you have up to 512 kilobytes of flash, 32 kilobytes of RAM, and up to 724-bit sigma deltas, which allow you to have up to 3-phase metrology plus tamper detection. Also, there is a integrated AS128 hardware accelerator, which is available on some devices, and an integrated comparator. One feature on the RTCC module in the 3-phase E-meter SoCs is that you can actually log events. So for instance, there's RTC cap pins, and whenever there is either rising or falling edge on the RTC cap pins, you can log the time where that occurred. So for meters, this could be used by having a switch that is triggered whenever you open the meter case. And whenever that is triggered, then you can log the time where the meter has been opened. The Sigma Delta 24B module has many enhancements from the previous Sigma Delta modules. It has a dedicated 32-bit result register. Previously in other families, you had a 60-bit register, and you have to read, then toggle a bit to read the rest of the 24-bit value. Also, another feature is that the modulation frequency has been increased from 1 megahertz to 2 megahertz. This allows you to have a higher sampling rate, and there's flexible OSR values. Also, there is a bit stream output from the analog modulator that you feed out, and you can also feed in a bit stream input to the converter to be used with the digital filter. Also, whenever a converter is idle, it is automatically turned off and turned on whenever the converter is triggered.
Could you tell me what the bit stream output is? I don't
Yes.
understand that.
So the Sigma Delta has two parts. The first part is the modulator, and the second part is digital filter. So the bit stream output is actually the output of the modulator that's fed to digital filter. So you can output that to a pin, and you can use another digital filter.
Oh, really? You can output that to a idle?
Yes.
Is this working? Yeah, the digital filter that we use is actually pretty common across a lot of TI. It's the sine cube filter. A lot of the ADS parts use it as well. So if you just have an external modulator, you can feed that in and use the same digital filter internally in the MSP.
There's a 64 and 128 PGA gain option, and you can trigger the module externally from the module itself, or trigger other modules, such as the ADC10. And actually, you can use this for a 3-phase solution whenever you have the 673X devices. By triggering, having the Sigma Delta trigger the ADC10 and having the voltages on ADC10, you can have a 3-phase solution. This slide shows the high-level comparisons of the different Sigma Delta family modules. in different families. The preload register, which I'll talk about later, the register limit has been increased from 256 to 1024. And also there is a temperature and battery supply measurement, which is actually available on the Sigma. It's not available in Sigma Delta 24B exactly, but it's available in those chips via the ADC10 modules. So, are there any questions about the Sigma Delta so far? Okay. The LCD-C module is the module used to drive the LCD. It can operate a MUX mode, drive up to 320 segments. Another feature is that you can enable or disable a segment individually from other segments. So for instance, like in the other family, you have to actually enable or disable segments in groups of 4 or 16. Another feature is that there is a, if you want to blink a segment on LCD, there's actually a special register to do that. So you don't have to manually set a bit in the LCD regular memory registers and turn it off. And the rate at which you blink can be programmable in software. Another feature is that by changing the setting for the charge pump's voltage as output, you can provide contrast control. There's also increased dividers for configurable frame LCD frequency and a dual display memory. So since there's blinking registers, register memory, you can use either the regular register memory or the blinking register memory as the memory used to turn on or turn off segments. And you can actually even alternate between them by using at a rate determined by the blinking frequency. Another feature is that whenever the necessary capacitor for the charge pump is not available, it could be automatically disabled to prevent damage to the device. And there's actually even a flag to determine when that case has occurred. There's also interrupt capabilities and external charge pump voltage options. So in the RTC module, there is a clock that is output that could be used for calibration. Based off of the deviation of the output clock from the ideal value, you can determine what the error in PPM is and update a compensation register to account for that. There's also a temperature compensation register, and based off of crystal's frequency versus temperature drift characteristics, you could calculate the error based off of a temperature reading. And once this is calculated, you can dynamically update the temperature compensation registers to account for this error. Also, the RTC module operates in calendar mode. It provides seconds, minutes, hours, day of week, month, leap year, corrected year. And these registers could be displayed in either binary coded decimal format or binary format. So if you want to display December, you can either display as 0x12 or 0xc. Another feature is that there are flexible program alarms, and there are multiple alarms. You can have alarm from 0.5 hertz to 16,384 hertz, or you can have an alarm every minute, at noon or at midnight. Another feature is that you can have an alarm trigger so that whenever a certain trigger is met, then an interrupt can be generated. The RTC module also operates in LPM 3.5 mode, and there is a separate voltage supply pin, AUX-VC3, which can be used to power the RTC module. So for instance, whenever there is a power outage, you can still continue to have the RTC running despite the rest of the chip not being powered. Multiple interrupts that are available, and there's also the external event capture feature that I mentioned earlier. This shows the differences between the RTC module and other RTC modules. The frequency adjustment range of the RTC module is plus or minus 240 ppm, and it can also adjust as small as 1 ppm. And the calibration is actually performed over a period of 1 minute. The aux module is another important module in the 67XX emitter SoCs. With the aux module, you have user-defined threshold, and whenever you're running off of a power supply, and let's say the power supply drops below a certain voltage, you can set it so that it automatically switches to another power supply, one of the auxiliary power supplies. And that, or you can manually switch between them, and that's actually used with the AUX-VC1, AUX-VC2 auxiliary supplies. The difference between AUX-VC1 and AUX-VC2 is that AUX-VC1 can be selected during startup time, and AUX-VC2 has an internal charger. So you can actually connect a rechargeable battery on AUX-VC2 to charge it directly from mains. AUX-VC3 is used to, as I mentioned earlier, to power the RTC and also the 32 kilohertz crystal oscillator and backup RAM. So this shows the block diagram of the AUX module. The VA-sys is the voltage that that's used to supply power to the analog modules, and the VD-sys is used to power the core I/O, the digital core. And VA-sys can be either selected from AVCC, AUX-VC1, or AUX-VC2. And VD-sys can be sourced from DVC, AUX-VC1, AUX-VC2. One thing to note is that if AUX-VCC1 is selected for VD-sys, then that same supply is also selected for VA-sys. So that covers the AUX module. Are there any questions so far about that module? All right, this shows a single-phase E-meter using the F6736 with tamper detection. And you have the CTs as the current sensor on the line channel, and you have the shunts as the current sensor on the neutral wire. And based off of if there's a high deviation between these two types of currents, this can indicate if the meter has been tampered with. And also you see the voltage divider, this part of the diagram, and then there's also the anti-aliasing filters. So in order to achieve good accuracy, meter calibration is necessary and is mandatory for every meter. Meter calibration corrects for any inherent errors. There are multiple types of calibration that can be performed. There's gain correction, there's offset correction, and there's also digital phase correction. And with digital phase correction, that is used to account for any additional delay that's not due to the nature of the load. And the reason why this is important because if there's a load, especially whenever you have a power factor, a lower power factor, this delay could more adversely affect accuracy. And whenever you perform calibration for best accuracy, you should always use a generator and reference meter. And the generator would supply the voltage and current to the meter. The meter would use the voltage and current and based on that calculate power and output pulses. The reference meter would use these pulses to determine what is the error of the meter. And once this error is calculated, the user can then update the calibration parameters as necessary. There are two types of calibration that can be done, single point and double point. And single point, only the gain is calculated, and double point, the gain and the power offset are calculated. And so whenever you use the CT, there's an additional phase shift that is introduced. And this could adversely affect accuracy, as I mentioned earlier. For instance, a phase error of 0.01 degrees could cause a noticeable difference of 0.03% at a power factor of 0.5. As a result, phase compensation is needed, and there are two ways to provide this phase compensation. The first way is to have a simple FIR filter, and the second way is to use the preload register to delay the sampling instance of a particular converter with respect to other converter.
Wouldn't the FIR filter slow things down even worse?
Yes, because you have to do calculations. And actually in our implementation, we use the preload values. So the preload register is 8 bits wide on all the families and 10 bits wide on the Sigma Delta 24B module. And this is used to intentionally delay sampling instances of a specific converter with respect to So the preload register allows you to delay the particular timing of a converter with respect to other converters in the same group. And the delay of the preload register is in units of modulation clock cycles. So for instance, if you're to write a value of 8 to the preload register, that would cause a delay by 8 clock cycles of the modulation clock. So in order to calculate this in terms of degrees instead of modulation clock cycles, first you calculate the delay resolution degrees, which is 360 multiplied by the mains frequency divided by the modulation clock frequency, and then you multiply this by the preload value to get the amount of delay produced by a particular preload value. So a host PC can completely automate a production calibration run, and in this scenario you would have a host computer that controls a host interface to have a source that's generated to produce voltage and current. And based off of the voltage and current, the meters would calculate power and output pulses. And the reference meter could use the pulses to determine what the error is and feed it back to the host interface for any actions to be taken by the users. So this covers the lecture portion for the most part. Now Bart's going to talk about the lab portion.
I'm sure this is the part that everyone's waiting for. Get to play with high voltage metering EVMs, right, that are laid out around here. So the idea here is that we're going to go over the F6736 EVM that is brand new to the e-store. So if you want one of these, go to the e-store and get it. Contact sales support however you want to. They are fully available in quantity. I highly recommend them to everyone. So if you ever have a customer that wants to get their feet wet with energy metering, this is available now. So a few of the features that we have on this guy, and you can kind of correlate it to the one on your desk, just the color is different, that's the only change. So we have the F6736 host processor on here, 160 segment LCD that was custom designed for e-metering for our purposes. We have a fully isolated RS-232 port on here, the full 4-wire JTAG implementation, all the power supply selection jumpers, a built-in cap drop power supply like I mentioned earlier, so it's not isolated from the power supply design point. So that means that if you connect this to high voltage, don't connect your JTAG. Don't connect anything unless it's to an isolated port, or else you're going to blow your computer up. As you can see here, we have the voltage and current front ends. So this little section here is the voltage divider and filtering, and these are two the current supply inputs. So this will support 2 current measurements and a voltage. So it'll go up, it'll do the tamper detection as McCray mentioned earlier using a shunt resistor. We also included the RF EMK headers. So if you want to stick Zigbee on this, or any of the LPRF chips, or Wi-Fi, or heck, we have GPS if you wanted to put it on there, it'll support all those, it's all standard. So if you take this to a customer, the one thing they're going to expect and ask right off the bat for metrology is how accurate is this? And so we can say we offer a 0.2% solution across the bat. It meets full ANSI and IEC specs. So what they're going to look for primarily here is the error at 0 degrees. So whenever your voltage and your current are in phase, this is the error that we can expect at 0.05 to 100 amps. So we test this in our lab with a reference meter. Regrettably, we can't do that here. We don't have the accuracy with the tools available. But back in the smart grid lab, we can verify all of this data. We also inject 0 degree and negative 60 and 60 degree phase shifts, so positive and negative. So where we have the current leading or lagging. This can be difficult for some meters to measure, and we can still hit the same accuracy requirements across the full spectrum here.
3% or 0.2%?
0.2. Yeah, 0.2. Some of these, we have other solutions that are more accurate as well. So if we have options for those as well. We have some that are less accurate and cheaper. So we cover a wide gamut here. So if you have someone that's doing kind of sub-metering and only wants maybe a 1% accurate solution, or even 5%, we've seen some of those. We have some much cheaper chips that are able to do that kind of range. So this is, like I said, there's a lot of features that McCray went over on this chip. So I'm going to admit right off the bat, it's not super cheap. So you're not going to be able to match value line prices on these things. But to get these kind of results, you need the high-end analog and you need the fast core to run all these computations. So this is what it's going to be coming out of the box whenever if you're going to take it to a customer. So for the e-metering customers, they're going to have the test setup and the reference connections to be able to do this kind of thing in their labs. So we have right here the voltage inputs are on these two terminals, and they're separated physically from the current inputs. So this is a safety thing, first off, for whenever you're doing design and test of these meters, to have these two separated so they're fully isolated from each other. Excuse me, but a lot of the reference generators that you see are going to generate these separately anyway. So it's a good idea to have these separated on the EVM. It makes it really easy to connect to some of the reference setups that are out there. And this is it connected to the one that we have in our laboratory. So you can see we have the voltage inputs are connected separately from our high current input. So this is 3-gauge wire, I believe, that's going into these things. So we source 100 amps into these terminals, and you can tell they get warm. The thing will vibrate sometimes at these high currents, but it's designed for it, so don't worry too much about it. You see right here, I have the lid off, and this big blue thing, that's the current transformer. So these are rated to 120 amps on these EVMs, so you have a little bit of headroom to play with if you take it to a customer and show them. So if they go in and plug it in, they'll be able to source what you would definitely see inside a house as far as residential meters go. I mentioned before, we have to do low voltage here. TI counts anything above 50 volts is high voltage. In our line of work, pretty much, I guess you got to be around 240 before we really consider it high. But TI's rules. So what we have here on your desk, you'll see there's the wall wart power supplies. Those are all 24 volt. So we had to make some modifications to the EVM. So there were some equations earlier, and you can download the slide deck to get them. And it showed how to tune that voltage divider in order to get the right input versus output range. So we've changed the resistor on these guys for the voltage divider. And we've also changed the burden resistor on these EVMs to match up with the lower current, so we can definitely get some measurements out of it. Otherwise, it would be way below kind of the minimum threshold that we can detect. And for the burden resistor, there was another equation as well earlier in the lab to kind of calculate that. You'll also see on here that we don't have those two separated anymore. So since we're actually connecting this to a line with a load, we have to have everything in series. So whenever your mains comes in here, we're using this terminal on the EVM, comes through the CT, so that's in series. It'll come out through a test load on these two, and then back in via this neutral wire to come back out. So a few hardware modifications were made to get these things to work. Just simple things. So at the customer, the high current will still go into the right-hand side, the voltage will go here, so just keep that in mind. And you might also notice that they're magically on right now. That's because the cap drop supply was tuned for 110 to 240 volts, so there's actually batteries in these. We cheated a little bit, but it'll still work for today, so we can get some measurements out of these and walk through the process. So the first thing, whenever you're going to if you take this to a customer, kind of the out-of-box experience, if you're going to connect it to a high voltage setup, find the RS-232 port. That's going to be your primary communication link with the EVM. They're going to come pre-programmed, but just make sure you find that port on there and get it connected to, if you're going to connect it to a serial link, straight to a serial port or to a USB port. That port is fully isolated, so you don't have to worry about blowing up your computer if you're using that RS-232 connection. And then secure any high current inputs. So if you're going to have to crank down on those screws to make sure that they're really secure if you're going to be pushing 100 amps through this thing. And then the same with the high voltage inputs. I lost my mouse. There we go. So make sure that those are securely connected if you're going to run this onto a test setup. So before you go, make sure you familiarize yourself with this EVM and all the features of it and kind of where things are so you're not fumbling around with it. So as many of you know, you probably don't have a COM port on your computer anymore. I think we're all living in 2013, or I guess some of the machines that ASMK gives out are a little older. But so what we do is we use, and you'll see them all on your desk here. Well, those who have one in front of you. We use USB to serial port converters. They actually sell these that are isolated. These are just cheapos. I think I got them all at Fry's, so no big deal. If y'all actually want to start plugging these in and using them, the USB drive that I passed out had the drivers on there, so I'll show you real quick. So there was this 6736 package. Oh, nope, sorry, the USB driver. So there's a driver in here. If you haven't used one of these before, there's just a prolific chipset, so they're all pretty much the same. So if you haven't used one, you can go ahead and install the driver and get these set up. It's the the Vista Windows 7 version. So if you have a different OS, regrettably I don't have the driver for that one with me. So whenever you plug it in, if you have the driver installed, well, if you open up your computer manager, or hardware manager, I'll just go ahead and do that from the get-go. So just right-click on your computer and go to Manage, and yes. And so there's some important information. We're going to need to know what COM port this is. The software that we use for calibration isn't smart enough to kind of figure these out on its own at this point. And if you open up your COM port devices here, so just COM and LPT, you can see there's a prolific USB to serial COM port. And so on my machine, that's going to be COM 48. So that's important to note down at this point. And also in that folder with the package, if you go to this F6736 package, is any, oh, I can hold up it. If, just tell me to stop if anyone needs to. Okay, I'll stop for a second. If y'all guys want to go. I have some assistants here as well that they can help you point you in the right direction if there's anything that's going wrong. So this is just, we're just trying to secure a connection to the meter from our calibration software. So. Peggy, are you the only one that's holding us up? So if you go into the F6736 package here, this is actually what we're going to be providing with the EVM. So if you go download the app note, this is the software package you'll get. So this contains our eMeter toolkit and our energy library software. That's all pre-installed on these. So right now all we really care about is this GUI 2 folder, and this contains our calibration GUI. And now there's an XML file in here. And if you open that up and edit it with, I use Notepad++, whatever your editor of choice is. And so what we're going to do is scroll all the way down to the bottom.
Which folder was that in?
Oh, sorry, yeah, I'll go back for that, that's fine. It doesn't, what did it do to it? We have some CDs around as well, see if there's a different one. Do you have 7? Do you have 7? Oh, we have some helpers going around that can. Yeah, build your own e-meter.
Okay.
Build your own meter.
Yeah.
And then F6736 package.
Okay.
And then GUI 2. So this is the second version of our GUI. That's what the 2 means. And so if you edit this calibration config XML file, so this contains all the data that the calibrator requires. And it looks like mine's already set to 48 properly. I promise that wasn't intentional, that just happened. Typically my computer likes to give these things random numbers. So since your meter's already powered, as the LCD is already running, so you can just go ahead and plug this guy in. And at this point, if you run this calibrator.exe, it should open up. And so if your COM port's connected, if it's a real COM port, it'll open up. And if it's talking to your meter, you'll have a green light. So we'll go ahead and make sure we can get everyone to the green light stage at this point. Okay, well it looks like everyone has a green light now. Well, they're getting moving that way. So for those of y'all with the good green light, click on it. So this is what you should see at this point, unless you've blazed ahead and started plugging stuff into your meter, like Peggy's doing.
Oh man.
So this is kind of the typical readout you'll see from one of our one-phase meters whenever you go in to calibrate it. What this does is it lets you see all of the metering parameters that it's currently reading. So as you can see, we got RMS voltage, current, active, reactive, apparent power, power factor, frequency. We have the V to I phase shift, any residual voltage that we have coming into the ADCs. So anytime you want to look at what's going on the meter without waiting for the LCD to refresh, you can go right here. So these are limited though in their accuracy since we only have a few digits coming through. So these are meant for the 50 to 100 amp range kind of readings. So what we're going to be doing is much less. So we're going to have limited accuracy due to that. Just a heads up, we're not going to be able to calibrate these things to the sub 1% levels. Go back here. So this is what you'd see if you had a 3-phase meter set up. So this is phase A, B, and C, and you can see the whole thing, it enumerates just the same as the first one, it's just times 3. So I think we still have a few more people going to get this. Once the, Kirpa, you got them? Okay. Nope, I guess I can go to the next level. So what we're going to do here is calibrate the meter for voltage, current, power, and phase shift. So these are the kind of the key elements. So if you get one of these out of the box, it's not going to be calibrated. It'll have some rough values. It might be close, but it's not going to be near meter grade accuracy. So what we have a reference source. As you see on your desk, there's probably a 24 volt AC wall wart. I think every meter had one put out there. So that's what we're going to use as a source. We also have a couple reference loads out here. So there's some 1%, Joe? Okay, sorry. There's some a 1% big wire wound resistor. So that's what we're going to use for our 0 degree phase shift resistive load. And then there's also a big inductor with a resistor hot glued to the top of it. And that's how we're going to simulate a phase shift on it. So we're going to use these known values, and then we're going to calculate what's expected to come through and calibrate the meter to make sure that we can measure that correctly. So the first thing is to make sure that you don't have voltage connected. I'm assuming no one's gotten to that point yet. So if you're going to be doing this actually at a customer site or in your lab somewhere, if you touch the meter, unplug it. Just disconnect any high voltage going to it. So we're going to try to emulate the same thing. These are still, 24 to 30 volts, so it can still be tingly if you get too close to it. Just be very careful out here. So the first thing is that you can connect the voltage source. So I mentioned before the 2 leads on the left. Hopefully people can actually see me up here. I know I'm about a mile away from y'all. So if you can connect the voltage source to these 2 leads, it's AC, so it's bipolar. It doesn't really matter which way you go on here. So since those of you who want to plow ahead, if you haven't done that already, go ahead and connect the 2 wires coming out of your AC source. Yeah. And then connect a test load. So you don't really want to just, on this one anyway, the way we have it set up, we don't want just voltage flowing through. So you can go ahead and connect that reference resistor on the other side. Okay, so there we go. A voltage source and a load, and it's not plugged in yet. Remember that. So it's just red so y'all can see it. So I'm going to go ahead and set this up here by my computer so that I can get it plugged into my RS-232 port. So make sure that your COM port's still connected. And if you've gotten this far, and everything is nice and secure on here, and I don't have any other power. So you can go ahead and plug it into your AC source. So there should be surge protectors. I know you might have to unplug your laptop to get the brick to fit in there, but I think we should be able to last this long. So once you plug that in, you should see some voltage reading and some current reading, and these should start populating with data. We haven't calibrated it right, so these are going to be incorrect at this point. So whenever the software is running, it can take a while to actually settle since there's digital filters. It can take a few cycles for those to settle out. So if there's a drastic change in the calibration values or into the data, the software detects that, and if it's red, that means it still has to settle out at the new value. So whenever you do calibration, you'll set it to a value and let it stabilize so that you have good, clean readings. So whenever these values are green, that means that they're pretty stable. Sometimes you'll get a few glitches if it's kind of moving around a bit, but for the most part, that's what we're looking for here. So now that we have power coming in, I would like people to treat these as if they're high voltage. Right now, I know it's only 24 volts coming in, but if you're sitting down with a customer, it's probably going to be 120 or 240. So this is where you hands off the meter and only talk to it via this calibration GUI here. If you do have to get close to it, we have the probes here that we're going to be measuring in a bit. So make sure that you're really careful whenever you get in there. You need to make sure that you don't accidentally touch any of the high voltage sections. So the next step here is that we need to know what the actual voltage is coming in. So there should be a multimeter at everyone's workstation. And I brought my own. You might want to do the same. Actually, we highly recommend it. Bring your own meter. Make sure that you can validate connections. Make sure everything's secure before you move too far forward with these. So these meters should have a 200 volt range, which is the best we could do with getting a bunch of these out. Yeah, for a $2 meter, that's what we got. And so you can use this to measure the voltage that's coming into the meter. And so we're going to use that as a calibration point. So typically if you have a reference generator, it's going to tell you exactly what your voltage is so you don't have to touch it. And that's ideal. It's going to force the voltage, it'll make sure that it's constant and stable, so you won't have to measure it like this. But for these purposes, we need to at least know what we're dealing with at the voltage level. So mine coming in, if I can get a connection on here. So mine is 26.995 volts, which is obviously different than what my meter's reading up on here on the screen. So whenever you measure that voltage, make sure you mark it down somewhere. Open Notepad, just write it down, because that's the point we're going to calibrate to. So all I'm going to do, 26.908 is where it's stabilized. So that's the voltage coming into the meter here. And as you can see, the RMS voltage here is clearly incorrect. So the next step is that we have to figure out what to enter into our GUI to tell it to change to the correct voltage. So once everyone has that, I guess we'll run around and make sure we're good on the meters, make sure none of those are too far off. Looks like everyone got to at least the reference voltage point, so what we got. So we need to be able to figure out from here what our meter needs to read for moving forward. So if I open up, actually I'll go back to my slides here, I actually have it worked out. So we have a simple equation here on what the value we enter into the calibration utility is. So it's our voltage observed over our voltage desired, so that's what we measured, minus 1 times 100. So I brought my calculator. Your computer has one built in if you haven't used it before. So observed in my calibration GUI here is 32.15. So what we're looking for, if you hadn't noticed, we're looking for the percentage change here. So what percentage is our reading off? It shouldn't be jumping around too much if you have a good connection on there. So mine is 32.05 divided by 26.908. Yeah, so it's your voltage here, the voltage in the GUI divided by the voltage you measured, minus 1 times 100. I'll put that back up here. So what this is going to give you is a scaling factor. Mine came out to 18.9. So that means we're 18% off in this field. That's not how our GUI works. Yes. We need it submitted in writing. So you'll notice a few buttons down here that we have access to. So one of these is manual calibration. So the GUI does support automatic calibration. We're not going into this, we're doing the manual stuff. So if you click on that, you'll notice a few fields here. And these are all in percent. So you'll notice voltage percent here. Yeah, that's where we're going to enter the number we just came up with. So mine was 18.96. So if you go ahead and hit update meter from this screen, so once you enter this calibration factor, update meter, and then you can go back to the other window, and you can see that it comes down to the value that you measured with the meter, the multimeter. So it's coming down pretty close, and you can fine tune it a little bit if you want as well. So rerun the numbers and it'll kind of narrow in on that value. The colors? So the green means a stable value. And the red is one that's kind of changing or it's unsure of. So if you plug in your power, it takes a while for that to stabilize. And so once it stabilizes, it'll turn green. And yellow is kind of an intermediate step. So it's best to calibrate these whenever the readings are green. So we know that it's taking nice, stable readings. And so it also takes time to re-inject. If we enter a calibration factor, it has to add that back into the DSP algorithm that McRae talked about earlier. So that can take a while to stabilize. So we just wait till they're green and go from there. So now the next one is our RMS current. So in a lot of cases, you can use a current meter to measure this and get a reference. They make these really cool clamp meters that it can just go around a high current cable and measure up to 1,000 amps or something. We don't have those here. Some customers will use a reference generator and you can use a reference meter to measure these. We're just going to calculate it. So we used a 1% resistor, so we have a really nice, stable, known load. And I'm pretty sure everyone here should know Ohm's law still. So we can use the voltage here, the 500 ohm resistor, and we can calculate the current that we need. So I know that my voltage is 27.08, and divide that by 500 ohms for our resistor. And it's 54 milliamps is what I want this readout to say. So currently it's about 256 milliamps, which is quite a bit off. So using the same equation we used before, move this out of the way. So our I observed of 256 milliamps on my case, divided by the actual current, minus 1 times 100. So mine is 372 for my new scaling factor. So in the next box here, current low, 372.7 for mine. So yours will be slightly different depending on what your meter's measuring. And mine was 370. So now we can see that this RMS current is exactly what we calculated for current to be. So is there anyone that, are we everyone on the same page here? So
you did that value into the current low, you said?
yes, into the current low field. So the voltage calibration percent, current calibration, and next we're going to move to active current or active power. So this is the factor that your customer is going to care about the most, is your active power accuracy. This is the one that we output via pulses, so we can get super high resolution measurements out of it. Again, we're just going to calculate it here to show how this scaling works. So I'm sure you all still know P is equal to VI. So if you take your voltage reading times your current reading, that's your expected power. So again, on mine, 27.04, 0.054 multiply, I'm expecting 1.46 watts. So that's my current instantaneous power. And so again, see, I think I might have another slide for this one. So yeah, we're using the same formula for before, P is equal to VI, enter the correction factor into the GUI again. So we'll go back to here so y'all can keep that on screen. So my active power right now is reading 39.27 watts. Same equation. And it's probably going to be pretty high. So mine came out to 1,905. So since it's such a pretty high number, whenever it comes down into the right range, it might still be off a little bit. So you can go ahead and adjust. If you run through the calculation again, you can get it a little bit closer and narrow it in on that range really, really well. This is something that might actually have to be done if you take it to a customer on their high reference meters as well. You might have to run through this equation a few times to really narrow in on the correct factor. So now it looks like everyone's gotten active power, voltage, and current calibrated as well as we can expect here in the room. So the next one, and I'm sure y'all can all see here, we have some trigonometry up here. We are going to do some phase calculations and calibration. So you might have noticed with the bevy of tools that have been placed out, in addition to that big resistor, there's a big transformer guy. This is actually a 1 Henry inductor. So we typically don't need these in the real world, but what we're going to do here with this is we're going to simulate an inductive load. So an inductive load would be something like a dishwasher or dryer or a pool pump or your air conditioning. And what it'll do is it'll put a delay on the current. So whenever your current and your voltage are out of sync, that can cause big problems for the grid. And they want to be able to know when this is happening. So in North Texas, during the summer, when everyone kicks on their ACs at 5 o'clock in the afternoon, that can put huge loads on the grid that it's very difficult to account for. So right now, Encore specifically puts giant capacitors to offset these big inductive loads on the grid. So this kind of stuff is very, very important with modern meters, so they can track this non-active usage. So they only bill by active usage as well. So it's kind of an interesting situation now that we're able to measure this kind of stuff with the modern meters. So the more data that we can get out of it, is the better that we can actually help the grid as far as robust infrastructure goes. So luckily, I did all this equation in math beforehand, so you don't have to. I saw there were some gasps out there. So like I said, this is a 1 Henry inductor and a 400 ohm resistor. So this is what it's going to do is it'll put our phase shift somewhere in the middle. It's just a ballpark. So the 1 Henry would be a perfect 90-degree phase shift, and the resistive load, as you can see, was just a 0 degree. And you might have noticed it was a little bit off. Those are actually wire-wound resistors, which has some, basic inductance, but it wasn't enough to concern ourselves with the active power. Anyway, we need to convert this 1 Henry into a reactive parameter. So we need this X sub L. So if you remember way back when, or if you've ever done analog work in the recent months, X sub L is 2 pi FL, where L is your inductance in henries, F is your frequency, 2 pi. So if you do all this math out, it works out to 376.9 ohms in the reactive domain. So if we calculate all this out, using this load here, and these are all pretty high quality parts, so they're going to be real close to this. So if it's not, we'll just use this as our number here. It's going to resolve to about 43.2 degrees. So with this, when you connect this load, it's going to induce a phase delay of about 43 degrees. So that's pretty close to 45, right in the middle of our 0 to 90 range. Now McCrae mentioned earlier that we use power factor quite often. So that's a real simple way with one number to be able to visually see what the grid looks like. What's the power factor of this appliance or at this building, anything like that. So that's simple. Just the cosine of 43.2 is 0.728. So what we're going to do is we're going to calibrate our meters to a power factor of 0.728 using this. So what that means is that we're going to inject a known power factor, and then anything else that's outside of that is going to be due to the CT that we're using. So we can calibrate that out. So let's get back to our dialogue here. So the first step, again, this is going to be more math here, but luckily this is also a little bit of intuition that you get as you go through this process. So we're going to use RMS voltage and current to determine apparent power. So go ahead and unplug your big AC adapter so that we don't have live voltage again. And then switch out the big power resistor. It might be a little warm, so be careful. And switch it out for our big inductor. Make sure that that screw that comes down on the terminal gets these ends nice and tight. So once you get that secured back down, you can go ahead and plug your transformer back in and re-energize the meter. So if you look at your meter status, you're going to start seeing active and reactive numbers that are a bit different than what you had before. So previously, the reactive power, I think, on those wire-wound resistors was about 0.1, while your active power was in the watt range. So now they should be approximately equal, but again, they're not quite right. So we're going to have to calibrate this. So again, the other one that we look for is here, the power factor. So my power factor is reading 0.63, which is a fair bit off from the 0.7 that we need. So if we go back to our meter one errors, what we're going to have to do, actually we need to calculate what we want this power to be. So we're going to use RMS voltage and current to determine apparent power. So same thing, since we have a different load, it's going to be different than before, but we can just go ahead and run that calculation again. And did I break it? Okay. So 27.31 times 0.03. So your RMS those are still calibrated. So don't worry, those are still going to be accurate. So I am looking for an apparent power of 819 milliwatts. So that's the point I want to calibrate to. I want to calibrate to that apparent, oh, no, not yet actually, there's another step. So we're actually going to calibrate to active power. I mentioned earlier that's the most important factor, so that's what we use for pulses. So if we want to accurately measure this, we need to know what our apparent power needs to be. Luckily that's pretty easy. So you can take the number you just calculated for apparent power, and if we look back at those equations way in the beginning, it's active power is power factor times apparent power. So 0.728 that we have here times the apparent power you just calculated. And that's the active power that we're searching for. So I'm looking for 596 milliwatts. 0.728 is our power factor. So I'm at 0.49 right now, and I need to be at about 0.59. So McCrae talked about it earlier. What we're going to use is the preload register on these sigma deltas to shift that point at which we measure the voltage and the current, so that we're going to remove the simultaneous value and we're going to offset them a little bit to compensate for any effects from the CT. So real quick here, there's another button that you might have seen down here. It's meter calibration factors. So if you go ahead and open that up, you can see your current voltage and current and active power calibration values. But another one down here is this phase. So this phase value goes from 0 to 256. So what we do, this instead of a percentage, what we do here is we increment it plus or minus to get it to the right value. So this is literally the value that's in that preload register. Again, so this is where it gets a little complicated. So rather than having a percentage, we don't actually have a good equation to just calculate what this preload register needs to be. It's a tough one to figure out, so you just kind of increment it and decrement it and narrow in on that value. So as long as you keep this between 1 and 256, you're not going to mess it up. So we found earlier that you got to knock this down a little bit, pretty high at first, since we're using such low values. So mine is negative 100 I'm going to start with. So I'm going to put this phase value down at about 123. So you got to enter that and update meter. And so it went down to 123. And you have to let these stabilize again. So you can see that the power factor went up. So we're up at 0.68 now. And we want to be at 0.72. So we'll try to go down even lower. So let's do another minus 60 on mine. So we're down to 63. We'll let this stabilize. What was that? So this phase low, you enter a positive or negative value to add or subtract from this phase calibration data. Yeah. So I'm going to keep going down on mine. It looks like whenever I go down, my power factor is going up. So I'm going to go take my phase correction down even lower here. Sometimes on these calibration values, if you go too far out of bounds, there's not proper sanity checks on them. It lets you do whatever you want. And it is possible to overflow the buffers that we have internally in the MSP here, and you can set it to a negative number and not get back properly. So yeah, with these low values on our loads, it's going to be really tough to narrow in super close to that 0.72 that we want to get to. And so you can also see, so we mentioned earlier, our phase shift is 45 degrees. And way back in the beginning, again, we talked about the power triangle. So a 45-degree power triangle is going to be equal in active and reactive. So since we're a little off of 45, you can see there's just going to be a slight difference between these two. They're going to be very close to equal at this point, but they'll be slightly off. So this is a pretty good approximation so far of our phase calibration. So you can probably, as long as your power factor gets approximately close to 0.72 and your active power and reactive power are almost the same, but not quite. You're going to get about as close as we can get here in the lab, so, or in the building here. So whenever we're in the laboratory using a reference meter or reference generator, we can accurately inject whatever phase shift we want, and your customer could do the same thing as well. So if they're really interested in this kind of data, they're going to have the equipment, the test equipment, to put this in and accurately calibrate and measure this result.
Reactive the same, it means they're 45 degrees, and 45 degrees power factor is 0.707. So
Yes.
pretty much realistic.
Yeah, so the point, like Kripa just mentioned, the 45 degrees would be a 0.707 power factor, just cosine of 45. But we have 43, it's a little off. I got as close as I could with standard value components, so we're starting to run a little close to the end here. So once you have all this data inside your GUI, you can open up this meter calibration factors that I showed you before, and you can copy this out, record it for that meter. So if you're going to take it to a customer and let them help calibrate it or give it to them, make sure they save this off so they can return to these points later in the day. And you can also use these as kind of a golden reference value. So you can input these into the source code, program it to another meter in production, and you can get pretty close to your calibration points. So that really covers it for our hands-on lab. I guess we have probably another half an hour before the next session starts, and so we can sit here a little bit longer and tinker around with these. But I do want to go over some safety tips. I've been bringing this up time and time again as we've gone through this lab. High voltage is dangerous. Don't touch the meter. Don't connect things to the meter unless it's isolated. Whenever you're playing around with mains voltage, you have 15 amps of possible current coming in at 110 volts, so you can definitely blow up FETs, USB hubs, ports. If you're going to connect to it while programming, make sure all of your tools are isolated. If you're going to be measuring any kind of voltage on the board, make sure you're using an isolated or standalone system. So the little DMMs, that'll work. They're battery powered. They're isolated from the mains. But make sure you use some IC clips, hook them on, and hands off if you power that thing.
$1,000 with a ground loop. Plugged in my laptop, non-isolated debugger.
I didn't tell Scott, but I did the same thing. Yeah, I've blown up USB hubs, FET tools. I got one sitting on my shelf that's just black and charred. We've detonated a few boards. So if you do manage to get one of these and blow it up, just say a little prayer that you're still okay, and just feel yourself initiated into the Smart Grid Club. That's pretty much the first thing you got to do before you're a real member around here. So whenever you go into a customer with this kind of thing, there's some important questions that you need to ask to make sure that you really get a feel for what they're looking for. So do they want a black box solution? You know, that a lot of customers right now, they just want a simple standalone metrology engine. What we offer is full SoC solutions. We have some other products that can be used though as a black box system. So if they want just a little tiny chip that'll do power metering, we offer solutions that can be configured to do that for them. Do they want to do programmability? And if, then, you know, whenever you actually take something to their site, what do they need? What do they have to offer as far as test facilities? Are they plugging a power strip into a wall and essentially doing what we did here in the lab? Or do they have a full reference setup? Well, you know, what do they got to use to actually kind of help you demo these applications? And you guys are now more than familiar with the calibration process. This is something you can definitely walk through with your customers as well. It's always useful to carry a multimeter with you, so you can make sure that things are not energized before you touch them. You can make sure connections are solid. You can make sure burden resistor values are correct. You can make sure there's no shorts, things like that. Always check with, you know, make sure the system is safe before you start energizing it. And if these guys are going to be doing full metering technologies, they probably have a fair amount of experience with this. So make sure that they know how to use their test setup. They should be more than familiar with it at this point. So you need to make sure just talk with them really well, you know, and interface with them to make sure that they understand the isolation versus what we have on the meter. So again, don't touch it while the meter's running, even if it's ground. Neutral is technically a high voltage line. So ground on our boards is neutral. So technically that's dangerous. Don't connect a JTAG to it when it's running, at least when it's connected to mains. There are options for isolated USB FETs, but the TI ones are not. There's a company called Olimex. They'll sell you one, more than happy to. They even make wireless FETs. And then you can also use a isolated USB hub, and those work pretty well in addition to that. So also, you never want to connect these to the mains unless your customer is really, really willing to take that risk. But I would leave the room personally at that point. Like I said, once you connect this to mains, you're talking the full grunt of the grid behind that. You know, if you short something out, it's going to go and it's not going to stop. So if they do have an isolated setup, that's the best. If they have a variac or something on site that'll isolate them from the mains, that's the best way to do this. Right now, these little black transformers are isolating our boards from the mains, so you're not going to get that full burst through there. So again,
I always heard use a variac, but I don't know how to hook it up. Is it just you got the big knob on top, you got the variable AC windings on the end. You can literally just take those and run them right in here where the mains
Yep.
would be?
so you can set your variac to 1-to-1, so 120 in, 120 out.
And then you don't have to plug your PC, right?
Yeah, you're basically just using the variac as an isolation transformer. That's exactly right. It's still not a great idea. I mean, even if your voltage source is isolated, I mean, it's still a good idea to just play it safe. That's still a high voltage. You can get sparks, you can fry stuff. So a couple things you need to go in to ask whenever you go into a customer site. You know, what are they really looking for? Do they want a meter grade solution? Are they going to be making something to go on a side of a house or a business? You know, what do they need? Well, do they need 1%, 0.5%, 0.2%? What are they looking for? Ask what kind of sensors they want to use. What's their cost target on this? I mean, if you look at the current transformers we use on these boards, they're about $10 a pop, and that's in quantity. So these kind of sensors can get pretty expensive. But if you talk a shunt, that's about $1 a piece. So there's definitely a lot of cost trade-offs here. So now that you're aware of those, you can definitely go into the customer, ask them what they need. What are they looking for? You know, definitely offer the right solution to them. It's great to have a working demo like this. For our other product families, if you contact us directly, we can get you working demos for the other ones as well. We'll have more stuff on the e-store coming soon. So there's a lot of great tools that are coming out, and I'm sure you guys saw Marcus's presentation yesterday. We got a lot of stuff in the pipeline that's going to be great to be able to take it, show to a customer, sit it down in front of them. Here's a working solution. So if this particular EVM that we have on the e-store doesn't fit, let us know. We'll get you the right one. You guys know the advantages of the 430 over anything else. So always have that kind of stuff in your back pocket. Let them know, like, how is the 430 better than our competition? What can it do better than anyone else out there? Go in, and these are kind of the typical things you'll ask for a customer. Is this a new problem for them? Is it a new design? Do they have existing test setups and accuracy and calibration systems that we have to interface with? Are they willing to do this all new from the ground up? So this is a lot of information that if y'all take and get from them, bring it back to us, we can definitely help you find the right solution for the customer. So we've also noticed that some of them might not have the right fit. TI in the past hasn't had the best focus on the smart grid, so you might see some stuff from analog that's kind of a miscommunication, but that's all worked out now, so customers in the past might not know exactly what they're looking at. Make sure they have the latest tools in their hands, the latest information, the latest data. We put publications out all the time about this kind of stuff, so just check on ESP, and you'll have probably the most latest information. So a few things, this is kind of just the end of it here. So, we offer solutions at 0.1% accuracy and better at 2400 to 1 dynamic range, ultra low power consumption, so we can run on a battery for months at a time and be just fine. We don't put much load on the grid with our solutions, so if your customer is making energy meters, they need to be able to sell those to the utility. So if they can come in and say, our energy meters are the lowest power consumption on the market, that's a big selling point for them. It's a big selling point for us, and it gets our technology into their meters. We keep it simple. If you've seen some of our competitors, they have some complicated front-end circuitry, as you saw before. It's a chain of resistors at best. We keep these kind of things simple, and we let the software do the job for us. We let the hardware do the job for us, and it all works out. In the end, whenever we take this application in, some of the customers, they don't believe how simple it is. But whenever you sit it down and show them, here we go, 0.1% accuracy, it just proves it. It shows them right there. So we also have a lot of extra features on here that can be really attractive to customers. So some of our tamper detection features, extra ADCs, the extra sigma deltas, things like that really, really help kind of sell our solutions. And we've even come up with some crazy custom solutions for some customers where we combine a couple of these parts together. We use some extra functions in new ways. So with the MSP, it's still a programmable core. You can do cool stuff with it, and you can configure it however you want to. So if you come up with an interesting new design, we can definitely help you work with that and move it forward to the customer. So we can meet just about any need out there. So with that, I mean, if there's any final questions, let us know. We'll be here for a while. I mean, I guess we're 2 minutes over time, so don't want to stick around too long.